All right. Good morning, everyone. Sorry. I was like ready to go. Like, all right. And then all of a sudden I realized I hadn't started any of the meetings yet. So here we are. It's Monday. All right. Couple of housekeeping things to get out of the way. Um, I sent out an announcement this morning about exam three. So it was due tonight. I have extended the date until because I know not everybody had their homeworks graded, and perhaps not everybody has had their homework graded yet. But I did go through, and everybody that has not had their homeworks graded or hadn't, as of like, I don't know, 6 or 7 this morning, I went through and just put the answers there. If you got it clearly correct, then I might have put like you got 45 points for this problem, but maybe there's not a score for the next problem. So don't stress out about that. The point is, have the answers. If you do have questions, please come to office hours. I didn't have anybody at office hours today, so I'm guessing that there were no questions. Or you can come to office hours this afternoon, 5 to 5:30, if you do have questions about those. And I've reached out to my TA to make sure that he has those graded today, but at least you have the correct answers so that you can kind of go figure out what you did and all that jazz. Okay. Also, I do have a list of poll everywhere questions. Let's change that to anyone. So here is the link to all those poll everywhere questions that you have until tomorrow morning to complete. If you have trouble accessing any of those, please let me know and I'll fix that. There is also a live poll, which is just, a you're here kind of question. So I'll put that in both of the chats there. Let's see, was that it? Did I actually mention? Yeah, I did that. I did extend the exam 3 due date until tomorrow night at 11:59. So if you needed that extra time to figure out what you did on your homework, hopefully that gives you a little bit more time, a little bit more breathing room. So, okay, we ready to start talking about convection? All right, so there were a couple of videos that were sort of on the list to watch, and I think what I'm gonna do, I've got your, this would be page 5 of your heat transfer packet pulled up, because we're gonna be, the videos kind of go through how these equations were derived, but what I want to do is just kind of go through each one of those and just make sure that you know what each of those guys represents. So before we get too far, let's I'm gonna, since I have some room on here, put it right here. So convection, and we're gonna be talking about, for the first 2 days, I guess, we'll be talking about external flow over a flat plate. In your book, they also go over to flow over banks of tubes, stuff like that, but we will not talk about that. We're going to limit ourselves when we talk about external flow is flow over a flat plate. And then the last 2 days, I say 2 days, but we may kind of blend one day over another. But the last 2 days-ish, we'll be talking about internal flow. So external flow for the first part of the week, internal flow for the second part of the week. Okie dokie. And so this would be, what is this? This is going to be chapters 6, 7, and 8. So chapter 6, if you looked at it, is heavy. It's really heavy. And I'm not, I tried to distill everything in chapter 6 in the videos. So if you need to refer to chapter 6, great. But as far as like where your time would be spent, I would spend my time much more heavily in chapter 7 and chapter 8 when we get to it. Okay, so flow over a flat plate. So this is, like I said, external flow. Okay, so you've got flat plate, and sometimes they'll talk about this knife edge. All of the plates that we'll be looking at is going to be that case. So you're not going to have like this blunt edge that's going to be causing some kind of some strange flow effects over here. So we're going to have, here's our velocity profile coming in. So if you've taken fluids, this will be a review. Okay. So this is what we call the free stream velocity, and it's in the x direction. So we use u for the velocity in the x direction, we use v for the velocity in the y direction. Now for our purposes, the velocity in the x direction is going to be a lot bigger than the velocity in the y direction. We'll have, when it hits this plate, you will have a velocity in the y direction, but it will be much smaller than the velocity in the x direction, and so we're going to kind of ignore it. Okay, and then as soon as it hits that, right, you're going to have sort of effect, right? Okay, so out here, right here, this would be the velocity. Out here is the free stream velocity where the effects of the plate aren't felt. But right there at where it touches the plate, that's where you're going to have friction between the plate and the fluid. And so you will not, that's the no slip condition. Which is going to cause a zero velocity right there at y equals 0. All right. So you've got regions of laminar flow and turbulent flow. So if you watch the video, there's a nice picture. There's I think I pulled the figure from your book, but there's a nice picture that shows how that changes the transition from laminar flow to turbulent flow. So laminar flow is characterized by these nice organized streamlines. So a streamline, if you can imagine, if you were to put a little if you had some flowing water and you put some dye in it, then that dye, you would just kind of see a line as it was carried on through. If it's turbulent, it's just going to get mixed up because the turbulent flow is just characterized by those molecules just moving around kind of randomly. And so, yeah, there you go. So, smooth, orderly flow along streamline. Turbulent flow is chaotic, right? Chaotic, random, mixing, right? There's no distinguishable streamlines that you'll be able to see. And that transition between the two occurs where we have a Reynolds number. So transition, because it'll start out as long as you've got laminar flow coming in, and you don't do something like tripping the flow, and we'll talk about that in a second. So this is, it will transition from laminar flow to turbulent flow at our critical Reynolds number. So at our critical Reynolds number. So the Reynolds number, and it's defined down here. So the Reynolds number, it's defined in a particular location, and it's a dimensionless parameter, and you can find where it transitions from laminar to turbulent right here. And for a flat plate, that critical transition or that critical Reynolds number is around 5 times 10 to the fifth. If you watched the video, you see that there is kind of a range of accepted values. This is the one that you'll see most commonly used, but depending on the surface conditions of that plate, it could vary anywhere from 1 times 10 to the fifth to 3 million. So there's a good range, but this is the one that you'll see most often quoted in literature. Okay, so let's look at the other things as well. So you've got things written in terms of viscosity. So viscosity, kind of the thickness or resistance. It's the resistance to flow, but I think of it as, you know, something that's sort of thick and goopy. Yeah. When I think of viscous. But this guy right here, this is the dynamic viscosity. We've also got the kinematic viscosity, and the kinematic viscosity is just the dynamic viscosity divided by the density, and that equation is also up here somewhere if I'm not mistaken. Yeah, let me just kind of wait. Oh, what's that? Delete. Okay, right there. So the relationship is right there. Okay. There we go. Let's see. So 2 different ways of writing it. That XC here is just the location along that plate at which that transition occurs. Okay. We've also got some relationships for shear stress. So it should be no surprise, I guess, and especially if you've watched the video, it shouldn't be a surprise that fluid mechanics and heat transfer, when you're talking about convection, they're very much intertwined. And so you can relate the shear stress and the friction coefficient to the velocity gradient, and the velocity, which is also related back to when we talk about it, it'll be related to heat transfer. So that's why we have these a mention of the friction coefficient, because it's all related to one another. Another thing that you saw in the video, hopefully, is that there is a difference between local and average parameters. So let's take this guy right here. So you'll notice that there's not a bar over it, and the subscript has a little, it's like you see that tau, the shear stress, little s, comma x. So it's defined at a particular location x along the length of that plate. So that's the local shear stress right at that particular point. Oftentimes, really, you're interested in the average shear stress over the whole plate, over a section of the plate. And so that's this guy right here. Okay, so just be aware of that. If the problem asks you, well, we'll see how they ask us, or they're wanting us to get, you know, whether we're interested in the local parameter versus the average parameter over a section of the plate or the whole plate itself. Okay, let's talk about, oh, we also have boundary layer. This is the boundary layer thickness. And this is the thickness of the boundary layer at a particular, so it's a function of x, but at a particular location such that, say it's the thickness where you I'm not gonna completely erase it. It's the thickness, i.e. the y, the distance y, right? If this is the y direction and then moving to the right is the x direction, it's the thickness where u is 0.99 of the free stream velocity. And it's defined at a particular location, x, right? The boundary layer thickness at that point. Right, so if this guy right here is 99% of that free stream velocity, then your boundary layer thickness would be that thickness right there, right? We also have, so that's the velocity, the fluid flow velocity gradient. We also have, and I'm gonna just use the same thing here. No, I won't. We also have the, I'm gonna erase this if you don't mind. So that's the velocity boundary layer. We also have thermal boundary layer. Okay, so same kind of idea. You've got this fluid flow coming in with a velocity, free stream velocity, u infinity. And let's just say this is a hot plate. Make it red to kind of indicate that. And you've got fluid coming through, and it's coming in the uniform temperature T infinity, so the free stream temperature. Well, right at after we allow it to come to steady state, if I looked at how that temperature distribution goes, right? The temperature close to the plate is going to be in thermal equilibrium with the plate, like right at the surface of the plate. But as it goes out, maybe I should make those lines a little bit more. But as it goes out, away from the plate, we approach that free stream T infinity. So we define that that thermal boundary layer thickness a little bit differently. So same kind of thing, looks like an S, it's not. So this is the thermal boundary layer thickness, thermal. BL thickness, where, and what is it? It's where the ratio T minus T infinity over T of the surface minus T infinity is 0.99. Okay. Okay. So we do have a couple of parameters down here. Here's our boundary layer thickness, and you'll see that it's specific to a geometry. And these relationships down here, they're empirical relationships, and they're dependent on the geometry. So here we've got a flat plate, and it's also dependent on whether or not we have laminar or turbulent flow. You also have this little TF down here. This is the film temperature. Film temperature. So it's going to be the average temperature between the free stream temperature and the plate, the flat plate temperature. And that film temperature is the temperature at which you're going to evaluate the thermal properties of that fluid. We've also got the thermal boundary layer thickness right here for a laminar flow. If it's turbulent, you've also got some relationships down here as well for a boundary layer thickness. Let's solve the first problem because that's about all we need to handle with that. The only other thing that I might say before we go on to that is our Prandtl number. So our Prandtl number, it's defined up here. So Prandtl, Prandtl number. And it's, if it will tell you the ratio of viscous and thermal effects. So if your Prandtl number, if it's greater than 1, then the relationship between that velocity boundary layer and the thermal boundary layer will be such that viscous effects are much more important. And so the boundary layer formation for the velocity boundary layer, it's much bigger than that for the thermal boundary layer. If they're equal to one another, or I'm sorry, if it's equal to about, yeah. If this is approximately equal to 1, then so are these guys. Okay, and this is laminar flow, by the way. And those are about equal to one another. And then if it's less than 1, then the thermal effects are going to be more important or more predominant. So the thickness of that thermal boundary layer is going to be bigger than the velocity boundary layer. Okay, let's work our problem. And then we'll start talking about the heat transfer. Come back over here. Okie dokie. So it says, consider the following fluids at a film temperature of 300 Kelvin. So they're telling us what that average temperature is. So we don't know the surface temperature. No, we don't know the surface temperature of that flat plate, and we don't know the free stream temperature, but we do know enough information to get the film temperature. So all right, so there's our flat plate. Free stream velocity of 1 meter per second. Just going to use a little one arrow there, but this guy is 1 meter per second. I'll put TF is 300 Kelvin, but once again, this is the average. It'd be the free stream temperature plus the surface temperature of that plate divided by 2. And we've got several different fluids. Yeah, we've got several different fluids. Let me move this. We've got atmospheric air, we've got water, we've got engine oil, and we've got mercury. And for each of these guys, I want to find the velocity and the thermal boundary layer thickness. So I want, there's my velocity boundary layer thickness. And we want it a distance of 40 millimeters from the leading edge. So this would be at 0.04. I don't know why I've got A and B, or just A, because I certainly don't have A and B. Go away, go away, go away, go away. And this should be in meters. Perfect. All right, like I said, we've got a couple of different things. So Yeah, I want to color code this somehow. There you are. So let's make, okay, let's make our air green. Let's make our engine oil. I want to make him black. I guess it's really dirty then. Oil. Oh, I skipped water. And for mercury, okay. Maybe I'll make that oil gray. Should probably make him kind of a, I probably shouldn't make him dirty, but that's okay. All right. So the first thing that you need to do when you have one of these problems is figure out, is it laminar or is it turbulent? So that's the absolute first thing that you should do. So for each, is the flow laminar or turbulent at that location? At x equals 0.04 meter. Okay. All right, so let's figure it out. So for air, let's figure out what our Reynolds number is. So our Reynolds number, and if we forget, it's defined away from, it's defined on our equation sheet. So just, I want to continue sort of referencing our equation sheet. That way, when you need to use one of these gajillion equations, you know exactly where it is. So this is page 5 of that heat transfer packet. And I'm going to be using one of these guys right here. It doesn't really matter which one that you use. It really doesn't. I think I'm going to use this one. But you'll see it doesn't matter. I can look up the properties for density, dynamic viscosity, and kinematic viscosity. Doesn't really matter. But this just gives me one less thing to look up. Okay, so I do need to look that up, and it sort of looks like specific volume. I don't want it to look like that. There we go. So I've got the free stream velocity. I've got the x location, yeah. But now I need to look up the viscosity. So let's go look it up. So this is actually table A1, I think. Select. Go. It's not, wouldn't be. There we go. Here we go. Yeah, so table A4, that's where we're going to find it for air. And we're looking it up at the film temperature. So the film temperature is 300. You can see that we've got our density right there. We've also got our dynamic viscosity and our kinematic viscosity. Do make sure that you note that those values that are reported in the table have already been multiplied by either 10 to the 7th or 10 to the 6th. So when you write it down, you need to write down. So if I'm gonna use this value right here. I'm going to write it down as not 15.89 meters squared per second, but 15.89 times 10 to the negative 6 meters squared per second, because that 15.89 once again has already been multiplied by 10 to the 6. So 15.89. All right, so this is equal to 1 meter per second times 0.04 meters divided by 15, 8, 9 times 10 to the negative 6 meters squared per second. And that's going to give me a value of 2517. So if I assume, because remember there is a range of critical Reynolds numbers for a flat plate, we're always going to use 5 times 10 to the 5th. And that's what's written down here on your equation sheet if you forget. It'll be different, once again, for different geometries, but for a flat plate, that's what it is, 500,000. So clearly, this is laminar. Easy peasy. All right. Next one, I guess I've got engine oil. I'm going to use gray there. All right, so same thing. Reynolds number is U infinity times our X divided by kinematic viscosity. So 1 meter per second times 0.04 meter divided by, all right, so let's see where that is. That's, let's see if we can find it. I wonder if I can I search it? Nice if I could. Gonna do it? What? Oh, grr. If anybody finds it before I do, throw it in there. I'm gonna, there it is. Here, perfect. Found it. Good gracious. So, table A5. Here we go. And I'm evaluating everything at 300. So, it looks like there's that guy. And by the way, for air, I also could have pulled the Prandtl number out if I wanted to. I will make note of that at some point at the very end about why that might be important. There's those viscosities. This is the one that I'm going to use, and it's already been multiplied by 10 million. Okay. So 550. Go away, you. $550 times 10 to the negative 6 meters squared per second. If I plug that in, get 4.66 times 10 to the 4th. So laminar again, right? Because it's not greater than 5 times 10 to the 5th, still laminar. All right, let's do for water. I do have tables for water. It's actually the saturated liquid water tables, if I'm not mistaken. They're over here. They're a little bit further up. There's refrigerant. Aha, there we go. Perfect. So at 300, and remember you've got, just like in thermo, you had for the tables for water, you had values for if it was if it were a saturated vapor versus a saturated liquid. We're going to use the ones for a saturated liquid. Even though it's not a saturated liquid, we're going to make the approximation that it's approximately equal to those properties for a saturated liquid. So the viscosity is the one that I'm getting. So this is, there we go. So this guy right here, and it's already been multiplied by 10 to the 6, so it's going to be 855 times 10 to the negative 6. If I needed my Prandtl number, that's the number that I would get, but I'll just kind of make a note of, you know, yeah, I'll make a note at the end of what those Prandtl numbers are. So for water, Reynolds number, infinity times x, kinematic viscosity. So I've got 1 meter per second times 0.04 meter divided by 0.858 times 10 to the negative 6 meters squared per second. And I get a value of, oh, whoopsie, for the oil, I'm so sorry. This is the 4.66 times 10 to the 4th. Apologies. I mixed up my order of water and oil, and so what I've got written down in my notes is switched. Sorry about that. This guy is 72.7. Apologies. Okay. Okay. And then I've got one more. I've got my mercury, and I was using red for that. So for my mercury, got a Reynolds number. It's my kinematic viscosity. So 1 meter per second, 0.04 meters. I'm going to go ahead and give you this guy, but it is in your tables as well at 300 Kelvin. This guy is 0.113 times 10 to the negative 6 meters squared per second. I get a Reynolds number of 3.54 times 10 to the 5th. Okay, so yeah, clearly there's a difference between those two, but what do we notice? We notice that this is still laminar. Notice that this is also still laminar, right? It's pretty close to that transition, but it is still laminar. All right, great. And so now we need to figure out what was it? Boundary layer thickness is. So go back to our equation sheet. It's up just a bit. Okay. So table 7.7 on page 5. Right. Got laminar. What's the other one? This guy. Laminar, flat plate. Here's our equation. Here's our equation. Oh, I should have pulled out the Prandtl number too. It's okay. I got it. So let's do the velocity boundary layer first. So they're all laminar. So velocity boundary layer thickness. What was he again? So it's 5x times the Reynolds number to the negative 1/2, or 5x over the square root of the Reynolds number. So 5x over the square root of that Reynolds number at that particular location, x. And this guy, at this particular location, x. So it's going to require us to have our boundary layer thickness, or velocity boundary layer thickness, over the Prandtl number to the 1/3, or the Prandtl number times the negative 1/3. Okay. There we go. All right. So for air, and maybe I should put it up here I'll put also your Prandtl number, the same place that you got the viscosity term. So I've got a Prandtl number for air, 0.707. When in doubt, air, it's going to be around 0.7. So, the Prandtl number for engine oil is 6,400. And for water, got a Prandtl number of 5.83. And for mercury, same place that you got the viscosity. I know I didn't look him up, but he is in your tables back there, 0.0248. And it's a unitless parameter as well. Do keep in mind, most likely on your test, would be given the Prandtl number or the viscosity if you did it, but that's not necessarily the case. And so just be prepared to look in your tables back there and look up property data. And once again, that property data, when you're talking about convection, it needs to be looked up at the fluid's film temperature, average temperature of the surface, and the free stream temperature. Okay. Am I good? Okay. Everybody's quiet today. Everybody's done. we're over the halfway point. We're just ready for it to be done, I guess. All right. So for my air, this guy, I mean, it's just plug and chug. So I get 3.99 for the, and it's in millimeters, by the way. Right, so usually you see these things reported in something like millimeters, just because otherwise you're going to be reporting a really, really small number. Thermal boundary layer thickness at that particular location is 4.48. So I know I don't have to. Let's just kind of look at what this is like. All right, so for my, you could see that the boundary layer thickness, it's comparable. Maybe this guy is just a little bit, if this is our thermal boundary layer. This is our velocity boundary layer. So they're comparable to each other. Maybe I should have drawn them a little bit more closely to one another. But if we look at our Prandtl number, what was our Prandtl number for air? 0.7. So you could see that it's pretty close to 1, but it's a little bit less than 1. And so once again, the Prandtl number is sort of a ratio of the viscous effects over the thermal effects. Okay, let's go on to the engine oil. We're definitely going to have viscous effects. So for our engine oil, I get a velocity boundary layer thickness of 23.5 millimeters and a thermal boundary layer thickness of 1.27. So if we were to draw this on our plate here, see a much bigger difference, right? This is going to be your velocity boundary layer thickness, and this is going to be your thermal boundary layer thickness. Let me make sure that looks like a plate. And this should not be a surprise because our Prandtl number is so high. What was it? Our Prandtl number was 64 400. And if we say that that's a ratio of the viscous effects over the thermal effects, right? Clearly, viscosity plays a big part. And so, because it's so viscous, it takes more room for that, for the velocity of that flowing oil to reach the free stream velocity. All right. What's the other one? Got water. And once again, it's just plug and chug here. This guy isn't as, this guy ends up being 0.93. This guy ends up being 0.52. Right, the Prandtl number, it was, I mean, it's not huge, but it is greater than 1. And so, not surprisingly, you see that the velocity boundary layer is a little bit thicker than the thermal boundary layer, but it's not terribly dramatic. Now, when we look at mercury, keep in mind that Prandtl number, he was pretty small, 0.0248. So you would expect to see that thermal boundary layer be bigger than it is. So our velocity boundary layer is 0.34 millimeters, but our thermal boundary layer at that particular location is 1.17. So that's our plate. So that's our velocity boundary layer. That's our thermal boundary layer. Okay. I think that's all we want to say about that. Yeah. Okay. So let's keep going. Problem 2. All right, so, oh good, it's engine oil. All right, engine oil at 100 degrees Celsius, a velocity of 0.1 meter per second, flows over both surfaces of a 1 meter long flat plate maintained at 20 degrees Celsius. Okay, so this is our flat plate here. And then our engine oil comes in. And he's coming in with a free stream velocity, infinity, 0.1 meter per second, and T infinity free stream temperature of 100 degrees Celsius, and it flows over both surfaces. So, right, you're going to have a boundary layer formation on both sides. Now, it looks like our surface temperature, TS, is at 20 degrees Celsius. So do keep in mind, I'm going to start writing stuff down here. Do keep in mind that when we look up properties, it's going to be evaluated at the film temperature. So property data going to be evaluated at TF, which your average temperature is going to be the average temperature of 100 degrees, 20 degrees Celsius, which would be 60 degrees Celsius. And because I just looked in those tables where I found the property data for oil, I know it's in Kelvin. So this is 333 Kelvin. And I'll look it up in just a second, but I can already kind of draw what the velocity boundary layer versus the thermal boundary layer looks like just based on what I learned from the previous problem. So I know that the engine oil in the previous problem, that Prandtl number was really high. It was for the engine oil at 300 Kelvin, it was 6,400. Now it's going to be a little bit different number for at 333. Not much, but it'll be a little bit different. But still, your viscous effects are going to be much more important. So, right, this might be your velocity boundary layer. Maybe I'll draw like this. That's my thermal boundary layer. Okay, I don't mean it to look like it eventually reaches some constant. It doesn't. There we go. And then, once again, it's going over both sides, right? So whatever's going on the top is going on the bottom. And like I said, that's the relationship between the thermal boundary layer and the velocity boundary layer. Viscous effects are going to be much, much more important than the thermal effects. When I say that, I should probably tease that out a little bit more. Because the viscous effects, not important, but more dominant. So viscous effects will make it so that it takes much more space for that, for the engine oil to reach the free stream velocity. Okay. Now, what was I supposed to find? So I need to find some stuff. So I need to know the velocity and the thermal boundary layer thicknesses at the trailing edge, and the trailing edge is at x equals 1 meter. Okay. So the thermal boundary layer at x equals 1 meter, and the thermal boundary layer thickness at x equals 1 meter. And then I also need the local heat flux and the shear stress at the trailing edge. So I need something at a particular location. So this is not going to be an average parameter. It's going to be at a particular location. So you won't see a bar or anything. And when we say the heat flux, we're going to specify with a subscript where exactly we're talking about, right? If I just left it like that, I wouldn't put a bar over it or anything, but this would be the heat flux over the entire plate, maybe. No, this is going to be at a particular location, L. And then of course I want the shear stress, the surface shear stress right there at that particular location at X, L. And then part C is going to be asking for the total drag force and the heat transfer per unit width of the plate. So the width would be into the page. We don't know it, which is why we're expressing it per unit width. So drag force, we would use F with a little subscript D. And since we're expressing it per unit width, we'd do with a little like that. So it would be FD per unit width. That's what we're looking for. And then the heat transfer per unit width would be Q, little prime there, and that would just be Q per unit width, where the W is once again into the page. I will have to figure out, is it laminar, is it turbulent, because the equations for the boundary layer thickness and the thermal boundary layer thickness, as well as the other stuff that I'm going to need to find out, is going to be dependent on whether or not it's laminar or turbulent. So that's the first thing that I'm going to do. So say is the flow laminar or turbulent at X equals L, because that's what we're concerned about for part A and part B, and it will matter for part C, as we'll see in just a second. Okay. So I'm gonna figure out, okay, well, calculate my Reynolds number. Let's get a little color here. So our Reynolds number at x equals L, maybe I should put x equals L as opposed to just L. So this is going to be U infinity times times x. I'm sorry, I was like just all of a sudden over viscosity. So I do have it at the film temperature, so at 333. If I look up what that viscosity is, what that kinematic viscosity is, yeah, I won't flow through here again because it'll take me a minute. But if I find the, I think it was table A5, if I'm not mistaken, then I can find that viscosity. So this U infinity 0.1 meter per second. X is 1 meter. This guy at 333, I'll have to interpolate, but I do get a value of 86.1 times 10 to the negative 6 meters squared per second. Perfect. All right, let's keep on going, yeah? So I end up getting 1161. Okay. All right. So it's almost 11:15. Is anybody there? So if you're there, say, yeah, I'm here and I'd like a break. Oh, sweet. All right. Yay. Ish. Yeah. Okay, good. Yay. Okay, that makes me feel nice. Y'all ready for a break or you want to plow on through? Monday. You want a break? We'll take a break right now. We could keep on going. Doesn't matter to me. Let's do it. Let's do a break. 5 minutes on the clock. I'll see you in 5, okay? Thanks. Okay. We are ready. I also have a "Are ya back?" question. So, yeah. There's a little link in the chat. So, yeah. If you're back, say you're back. I'll leave that up for a while. Okie dokie. All right, so we need to figure out the boundary layer thickness. We figured it out. Oh, that the flow is laminar, right? And it's laminar because our Reynolds number that we calculated at x equals L is less than 5 times 10 to the 5th. Right, that might be something I could throw in my assumptions. I actually didn't have any assumptions that were listed, but I guess this falls into the category of something I am assuming, that the Reynolds, the critical Reynolds number is 5 times 10 to the 5th. Okay, and so it's laminar. So I have a couple of relationships for that, right? I have my boundary layer thickness, which is 5x over the square root of the Reynolds number. X being 1 meter, the Reynolds number being the thing that I just calculated, and so it's just a matter of plug and chug. I get 0.147 meter. I'll box that guy. And then my thermal boundary layer thickness is just going to be this guy times my Prandtl number to the negative 1/3. I didn't actually look up what my Prandtl number is. So this is evaluated, the viscosity was evaluated at TF, and so is this. So this is evaluated at the film temperature of 333. You can look that up in your tables in your heat transfer packet. So this ends up being, it's going to be 0.147 meter times the Prandtl number, and I get a Prandtl number of 1081, and then I need to do to the negative 1/3, and so I get a boundary layer thickness of 0.014 meter. And that's sort of in line of, not sort of, that is in line with what I've drawn up there preemptively, because I kind of knew that I was talking about something that was very viscous, and so I knew that my boundary layer, my velocity boundary layer thickness was going to be a lot bigger than the thermal boundary layer thickness. So that takes care of A, and now we need B. So B is asking for the local heat flux. So let's go into that. We haven't really talked about the thermal properties or the heat transfer coefficient and Nusselt number and all that stuff. We're going to do that now. So, well, let's apply. I know that the heat flux is going to be by convection, right? So I'm going to apply Newton's law. Of cooling, right? So this guy, oops. This guy at x equals L is going to be, it's H times delta T. So H times TS minus T infinity. So TS and T infinity, that's no problem because I know both of those. TS is 20 degrees. T infinity is 100 degrees, but it's that H that I don't know, and it's not a property that I got to just look up. I have to calculate it. And not only that, I need to make sure that I note that this is a local heat transfer coefficient. I'm looking at the heat flux at that particular location, x equals L. And so you won't have a place that you can look up these guys, but what you will have is formulas for the Nusselt number. So let's show how that stuff is related, and let's show where you can find how it's related. And we'll talk about those things. There we go. So you can see I've got NU with a little subscript. NU is the Nusselt number. This is the dimensionless heat transfer coefficient, and it is a measure of how much heat transfer is enhanced by conduction. So if the Nusselt number or is enhanced by convection. If the Nusselt number was 3, it means that the heat transfer would be increased 3 times what it would be with convection over what it would be if there were no flow and everything was just stationary. The fluid was just stationary, and so heat transfer would be only by conduction. Right, so if you had a stationary fluid just sitting on top of that plate, as opposed to it's flowing, the Nusselt number compares those two. So if it's 3, that means that the flow just means that the flow will enhance that heat transfer by 3 times. Okay, and it's dimensionless, right? There's no dimensions or no units on there. And it's related to that heat transfer coefficient. So this is the guy that we're going to use. So I'm going to write him down. So I'm going to write an equation for the local heat transfer coefficient, H at x equals L. And this is H at x equals L, and it's going to be KF over X, which X is equal to L, times that Nusselt number at X equals L. Okay. And once again, it's written as a local Nusselt number, which is equal to H at a particular location X times X over KF. That's the way it's written on your equation sheet. Okay, so rate. And I do actually have an analytical or an empirical solution for that Nusselt number. Let's write down what that is. So that KF, by the way, is the fluid thermal conductivity. So let's look at what that is, what the Nusselt number is. Nusselt number. Okay. So once again, we've got laminar flow. There we go. We've got laminar flow, and there's our local, oh, I'm sorry, that's for turbulent, isn't it? There we go. That was for laminar, but that's for a different Prandtl number. So this is our local local non-dimensionalized heat transfer coefficient, local Nusselt number. And it's for if our Prandtl number is greater than 0.6, and obviously that is the case here. We've got a Prandtl number of just over 1,000, so that's the one that we would use. So 0.332 times the square root of the Reynolds number times the Prandtl number to the 1/3. So let's go ahead and write that. So this guy, 0.332 times the Reynolds number, which we just calculated at x equals L, to the 1/2 times the Prandtl number to the 1/3. And we have those things, right? The Reynolds number, we calculated him to be, what was he? 1161. Got the Prandtl number, which is 1081. I haven't actually looked up this guy yet. So this is going to be evaluated at the film temperature, and you're going to look it up at the same place that you've got those properties, that property data for engine oil, and you're looking it up at the film temperature. And at the film temperature of 333 Kelvin, this is 0.14 watts per meter Kelvin. Okie dokie. Perfect, perfect. All right. So I guess a number would be nice there, wouldn't it? If I plug in all those things, I end up getting 16.25 watts per meter squared Kelvin. And so now I have enough information to plug that in. So I'm going to kind of, I got a lot of stuff here, so I'm going to put this in like a little happy bubble. Oops. Happy bubble, and then put this local heat flux right there at X equals L, ends up being negative 1300 watts per meter squared. And it's negative because, why is it negative? Okay, I think everything's okay. I was hearing some strange noises, just making sure nobody's screaming. Okay. I think everybody's good. Okay. But it would be negative because the surface temperature is less than the free stream temperature, right? So I've got that guy. Perfect. So that's part of B. But then the other thing that we needed to get what? Oh yeah, the local shear stress. So let's get that. So local shear stress, and we have an equation for that. We just have to know that we're talking about the local shear stress as opposed to the average. So if I go to my equation sheet, let's look at where he is. That guy right there. So that's the local shear stress. This guy right here is the local local coefficient of friction. And then there we go. Right there. Perfect. Is that right? Oh no. Whoopsie. It's up here. I had to look at the correct one. I don't know why I keep on looking lower. All right. So this is for a flat plate. It's laminar. The reason that the one, if I kind of looked a little bit down, I was looking right here, I think before, this is for turbulent, right? So that's why that one would not be the correct one. Okay, so let's write down those things because I need kind of two equations together. This guy and this guy. Okay. Okay. So this guy at X equals L is equal to CF. So this is local coefficient of friction, 1/2 times the density times U infinity squared. This guy is a property of the fluid. So at the film temperature, once again at 333 Kelvin, So that's TF. At the film temperature, that density ends up being 864 kilograms per meter cubed. And then this guy, let's put him right here. I get a CF, I get a friction coefficient of 0.664 times, or divided by the square root of the Reynolds number, or just the Reynolds number times -1/2. So once again, you just have to make sure that you get the appropriate equation. You need to make sure that you distinguish between whether it's laminar or turbulent, right? Yeah. But if I plug those things in, because I've got my Reynolds number, I get something, and I don't have that number, but I do have the final answer. So I've got a shear stress of, and that's going to be 0.0842, and it's Newton per meter. Oopsie. Okay. All right. So that's also B. And then C is asking for some stuff that requires us to get some average parameters. So the first thing that it asks is the total drag force, and then the heat transfer per unit width. So, okay. So drag force. Well, I've got these equations for shear stress, so maybe it would be useful if I related those things together, because shear stress, and we're going to be talking about the average shear stress, the shear stress across that entire plate, it's going to be equal to the drag force over the area. And keep in mind what area we're talking about, because it's going over the top and the bottom. So this would be FD, the thing we're supposed to be finding, times the area. So it's going to be width times the length. That's the area, but once again, it's on both sides. So it's 2 times W times the length. Perfect. And I'm actually looking for the drag force per unit width. And so, right, you can see this is just going to be FD with a little prime there over 2L. So I'm good there. But I also know that I can define this in terms of the average. Let's look at it. There, the average coefficient of friction, which if it's laminar flow and it's over a flat plate, you have to, yeah, laminar, flat plate, that guy right there. So it's averaged over the entire thing. So 1.328. So this is also equal to what's it again? There it is. Rho U infinity divided by 2 square. Okay. And then of course that average friction coefficient is, oh, nope, stop it, display fusion. Yep, I got it. You're good. This ends up being 1.328 times the Reynolds number to the -1/2 times rho, which we just looked up, and that's 864 kilograms per meter cubed, times the free stream velocity squared divided by 2. And so now it's just a matter of solving for this guy. So FD, this ends up being 0.337 you'll get newtons per meter. So make sure that you kind of go through and make sure that you could see why you should end up with newtons per meter. So that's the first part of C. And the last part of C is to find the heat transfer per unit width. And once again, this is asking for the Q over the entire plate. So, all right. So I'm going to be applying Newton's law. But I'm going to be applying it to the entire plate. Right? I'm not expressing, I'm looking at the entire plate, not just at a particular location. All right, so this Q, which is equal to Q over W, is going to be, all right, so I'll have H, and this would be the heat flux times the area. And the area, keep in mind, we've got heat transfer on the top and the bottom. So it's going to be 2 times WL over W. And so you can see those guys are going to cancel out. And so my Newton's law is going to give me that this is 2 times L times, and it's going to be H, but the average H value over the entire plate, times TS minus T infinity. And I'm kind of running out of room, so I'm going to kind of zoom in here and just write a little bit smaller. Make sure that you can see that. Right. So everything's, I've got L, that's 1 meter. I've got the surface temperature. I've got the T infinity. Is that H bar that I got to figure out. So this is the average heat transfer coefficient over the entire plate. And so this would be, and once again, it's on your equation sheet. Go look at where the same place that we looked at how the convection coefficient, the local convection coefficient, was related to the local Nusselt number. Same kind of equation applies for the average Nusselt number. So your H bar, it is going to be Kf, thermal conductivity of that fluid, times the average Nusselt number over the length of that plate. Sometimes you'll see a little L subscript, sometimes you won't. This is going to be over L. So I've got the thermal conductivity of the fluid. I've already looked that up. Remember, it was 0.14 watt per meter Kelvin. That was evaluated at the film temperature. Length is 1 meter. And the Nusselt number, got to look up the equation for that in that table of lots of stuff. So laminar flow, flat plate. All of these are for a flat plate, but I'm just kind of keeping on going back to that flat plate because it's going to be different for different geometries. So it looks like, yeah, that one right there. Flat plate, it's laminar. Prandtl number is definitely greater than 0.6. We've got engine oil. And so that's our average Nusselt number. So let's go back here and let's write it down. So this ends up being 0.664 times the Reynolds number to the 1/2, and it's going to be at that, right, the Reynolds number REL, right, because that would be at the length, times the Prandtl number to the 1/3. Okay. That it? And I know all that stuff. I've already calculated the Reynolds number at x equals L. I've already evaluated the Prandtl number at the film temperature. I've already evaluated the thermal conductivity. And so this is just a matter of plugging things in. I get a value of 32.5 watt per meter squared Kelvin. And so when I plug things in here, I end up getting negative 5200 watts per meter. So that's my, and that's watts per meter width of the plate into the page. Okay. All right. Let's move on to problem 3. Okay. Looks pretty when we like Christmas. Red and green. All right. So we have a flat plate of width 1 meter is maintained at a uniform surface temperature of TS 150 degrees by using independently controlled heat generating rectangular modules of thickness 10 millimeters and a length of 50 millimeters. Each module is insulated from its nozzles, from its neighbors, nozzles, as well as on its backside. Atmospheric air at 25 degrees Celsius floats over the plate, yada, yada, yada. Okay. Let's draw it, yeah? Back over. All right, I'm gonna zoom in because I feel like I write prettier. It's like kind of fat. There we go. All right, so here is our plate. Okay. And I think because they do reference how thick the plate is, and that will be important. So kind of draw it a little bit thicker. But we have got air. Air coming in. Free stream velocity of 30 meters per second and a free stream temperature of 25 degrees Celsius. And it's saying that that plate is divided up into different modules to that generate that internally generate heat in order to keep the surface temperature at 150 degrees Celsius, as opposed to it eventually coming into the equilibrium with the air that's flowing over it. So, right, here's a module. There's a module. Okay. On down until you, so I'm going to kind of like make a break here. And now I'm looking at this particular module. And in between each one of these modules, they're insulated from its neighbors. So insulated right here, insulated right here, and it keeps on going for however long, I don't know. But it is also insulated on this side right here. Okay, so the whole point of it is all the energy that's generated within this thing. And let's make sure we make a note of that. That's going to be our Q dot. Right. So our Q dot is going to be in watts per meter cubed. But what that leads to is it leads to a flux. Okay. Right, because if we did an energy balance, we would see that those two things are related, right? And we will have to do that in just a bit. Okay. Oh, and the dimensions of this, once again, so go. So this dimension is A, which is 10 millimeters, 0.01 meter. And the length of this guy is B, 50 millimeters, 0.05 meters. And we are analyzing a module that is 700 millimeters from the leading edge. So what they mean is if this is the leading edge, right, that distance right there, 700 millimeters or 0.7 meters. Okay, all right. And we do have some properties of the module that are given to us. So I'm going to look at those right now. So the module properties. Can I make that smaller? I cannot. Okay, so my module properties, I've got a K value. I know it's in the text of the problem, but I'd like to rewrite it because we'll also have the fluid properties and I don't want that to get mixed up. So this is 5.2 watts per meter Kelvin. Specific heat, 320 joules per kilogram K. So watch your units there. Density, 2300. This is already, right, sometimes we list CP or C and kilojoules per kilogram K, so you just want to make sure that you pay attention to those units. This is kilogram per meter cubed. So we're all good there. And then we also say that the surface temperature, no matter where, right, the surface temperature, it's 150 degrees Celsius, right? Might be a different temperature right there at the interface, like, right there at X equals 0 or Y equals 0, as it should say. So like this is Y equals 0. This would be Y equals A 10 millimeters. Yeah. Okay. We have the free stream velocity. I want to kind of keep everything nice and organized in my solution because I'm going to be actually looking for a lot of things. So I am sort of going to skip to the chase. So at the film temperature, we have, and that film temperature is 360 Kelvin. So it's the average of the free stream temperature, 25 degrees Celsius, and the surface temperature, 170 or 150 degrees Celsius. But at the film temperature, fluid temperatures or fluid thermal conductivity 0.308 watts per meter Kelvin. You have a Prandtl number of just about 0.698, and then we have a kinematic viscosity of 22.02 times 10 to the negative 6 meters squared per second. Okay. All right. Now let's go back here and see what we're supposed to find. So we are supposed to find, all right, so I need to find the required power generation. So in my figure here, I need Q dot, and then I also want to find the maximum temperature in that heat generating module. So I'm going to zoom in again real quick here. Bring that A over here. So I need Q dot, the amount of power that's generated. That's what I drew in that little box over there. So this is in watts per meter cubed. And I am also going to need to know the maximum temperature in that heat generating module. Now, it has been a while since we've, had to get the, apply the heat diffusion equation to a particular solid, but we're going to have to do that here, just FYI. So, and if I think about where the maximum temperature is going to be, is it going to be at the surface or is it going to be at y equals 0? It's going to be at y equals 0, right? The air is going to be cooling things down, but at the very bottom, you've got this insulation where you don't have, the heat doesn't have anywhere to go except, in the positive y direction. And so right at y equals 0, it's going to get cooled down. I don't want to say last, but right, that maximum temperature is going to be at Ty equals 0. So this was a lot of work to set up, but right, that's okay. I guess we're all good there. Okay. And then I'll throw my assumptions on here. A little bit of work to set up, but I think taking the time to actually set it up like this will help us a lot. All right. First things first. Before we do anything else, we need to figure out, is it laminar flow or is it turbulent flow? And so I think what I'm going to do is I could get the critical Reynolds number, or I could get the Reynolds number at 0.7 meters, but then I would also have to get it at 0.7 plus 0.05 meters, right? Because I'm interested in that particular little module. I want to know, is it laminar flow or is it turbulent flow right there? So instead of calculating the Reynolds number directly, what I'm going to do is calculate that XC, that critical X location, where the transition from laminar to turbulent flow occurs. So, solution. Right. So, here we go. Determine where XC is. Okie dokie. So, if we don't remember where any of this stuff is, right, this is page 5, and it's right there. That's what I'm looking for. So my XC, that critical location, is going to be the critical Reynolds number, 5 times 10 to the 5th, and I'm going to put it in terms of the kinematic viscosity. So let's write that. Okay. So my XC is equal to the critical Reynolds number times that kinematic viscosity divided by U infinity. And keep in mind, I've already looked up the kinematic viscosity. I've got the free stream velocity. This is just going to be, let me go ahead and zoom in here, make sure I write the right things down. This is going to be 5 times 10 to the 5th, that's my critical Reynolds number, times that kinematic viscosity, which I looked up at the film temperature, 22.02 times 10 to the negative 6 meters squared per second, divided by my U infinity. U infinity is 30 meters per second. All right. All right, so this ends up being something. Something. So this ends up being 0.367 meters, or 367 millimeters. And so you can see that transition occurs, right? He occurs somewhere around here. About there. And I know that because I just calculated him. So clearly the flow is fully turbulent over that module that I'm interested in. So any relationships that I'm getting have to be for turbulent flow. So that's important. All right. Perfect. Perfect, perfect. All right, so I've got that. Now I need to relate how that Q dot is related to my flux, because my flux I can apply to what's going on in the liquid itself by applying Newton's law of cooling. So that's sort of my train of thought here. So great, I've done that. Okay, I'm gonna try to put my directions in green. Maybe I can make it look a little bit more colorful. So we figured out that it's turbulent, but now I need to apply my energy balance. And I'm going to relate Q dot to Q, or maybe the flux. Whichever, you know, maybe one is going to be more useful than the other. I don't know. So remember what our energy balance looks like. And we're doing this just to the module of interest, right? Just to that one module at a distance 700 millimeters in. So we have E dot in minus E dot out plus E dot G plus, oops, not plus, equals the amount of energy stored, or the rate of energy stored. Now, if everything's occurring at steady state, this goes away. And in fact, that is something I am going to assume, so I should put the steady state. I think I also said that, probably should say, well, my critical Reynolds number is 500,000. All right, so that goes away. I clearly, if I look at that module up at the top, I don't have anything going in. So I can see that the E dot out is equal to the E dot G. So, okay. So E dot G, it should be in terms of watts. So this is going to be Q dot. But in order to get everything in terms of energy rates, then I need to multiply that Q dot times the volume. The volume being the area, times A times B, A, B times, and let's say that, you can keep in mind that this is it's a three-dimensional thing, right? Let's just say that this is the width, right? And it would be the width into the page. So not watts, but width. So A times B, right? This dimension times this dimension times the width. And then if I wanted to get that rate of energy out, it would just be, and I'm going to put it in red, it'd be the heat flux, the same that I've drawn in the picture way up at the top, times the area that it's going through perpendicularly. So the area that it's going through perpendicularly would be that width into the page times B. So B times that little W. So it doesn't really matter what I called it. It's just going to cancel out. And so is that B, actually. Okay. So now I have a relationship between those. So I know that that Q dot is going to be equal to the heat flux divided by A. So that's not my answer, but that's something that's useful, isn't it? Okay. So I've got that, and now I need to apply Newton's law of cooling. So and I am applying it just to that module, just to that particular module. Okay, so I've got the heat flux, and this is going to be H times Ts minus T infinity. So Ts is the 150 degrees, T infinity is 25 degrees. Now I have to think, is this a local heat transfer coefficient or an average heat transfer coefficient? And I might want to say, oh, well, this is, I'm looking at, you know, a particular location, but it's not at a particular location X. It's actually between two locations. So, right, the locations being at, right, this guy right here would be, if this was the length, if this was called L, then this would be, this is X equals L, and this would be X equals L plus B. So it's between those two values, and so it's going to be the average H value between those two values. So average between L, and I'll put a little L to L plus B. Okay, so here's where I also have to be kind of careful, because I might want to say, well, oh, I could just look that up. I could look it up because I know the average Nusselt number, don't I? Right, and I can relate that to the average heat transfer H bar coefficient. But I kind of have to be careful because this guy right here, oh, well, and it'd be the turbulent one, wasn't it? Wouldn't it? Not a problem, but yeah. So let me kind of step back just a minute, because you'll notice that you don't have, unless I'm missing it, you don't have listed an average Nusselt number for turbulent flow, but you do have a local turbulent value. This guy right here, mixed average, it takes into consideration that you've got laminar flow that transitions to turbulent flow. These average values, I know I'm looking at the laminar, I know, but these average values, they're taken from X equals 0 to the length of the plate that you're interested in. But here we're talking about between two particular locations, so I kind of have to be careful. This is what I'm going to use. So if you watched the video, you could see that we calculate those average convection coefficients for a flat plate by integrating from 0 to L, that local heat transfer coefficient, which can be related to the local Nusselt number. And here they were integrating from 0 to L, but we wouldn't do that. We would integrate from L 0.7 meters to L plus B 0.75 meters. So let's kind of take a step back. I know we're sort of running out of time, but I at least want to get to that idea first. So this H bar from L to L plus B, it's going to be 1 over the length that you're talking about, but the length that we're talking about is the length of that module, right? It's the length of the module, and the length of the module itself is b. It's b. And we're going to be integrating from L plus b, or L to L plus b. And then it's going to be the local heat transfer coefficient times dx. And you can relate that 1 over b, you can relate that to the local Nusselt number, L to L plus b. And that local Nusselt number is for turbulent flow. So your turbulent flow, you have an equation for that. Let's see where he is. There. Here it is. This guy right there. Turbulent local flow. Okay. Reynolds number is less than 10 to the 8th, right? What was it again? Oh, do we have it? Yeah, if I actually don't have the Reynolds number, do I? I've got it somewhere. We could calculate it. I don't have it right here, but 10 to the 8th is pretty big. We're not there. And our Prandtl number is not greater than 60. It's less than 0.6 or less than 0.6, right? We've got air. Our Prandtl number was 0.698. So it's on the low end, but this equation is still valid. So local heat transfer, local Nusselt number for turbulent flow is going to be oh, and this is going to be, I'm sorry, this would be where our Hx is going to be Kf over x times the Nusselt number at that particular location, x. So this is going to be Kf over x times the local Nusselt number, the local Nusselt number being 0.0296 times the Reynolds number to the 4/5, right? This is, I'm pulling it right off your equation sheet, times the Prandtl number to the 1/3. And you're integrating this with respect to x. Okay, we'll write one more thing to at least see where you're going. So that thermal conductivity of fluid, he can come out of the integral Kf over b. So can that 0.0296, I guess, couldn't it? And the Prandtl number. Actually, that's fine. Okay, so times Prandtl number to the 1/3. And we have our 0.0296. And then from integrated from L to L plus B, we've got our Reynolds number to the 4/5. And our Reynolds number is defined as U infinity times x over that kinematic viscosity to the 4/5 dx, we're getting there, equals, now some other things can come out, right? We'll have, I'm going to bring the 0.296 over here, 0.0296, sorry, 0.0296 times Kf over b. Prandtl number to the 1/3. Then we got some other things that can come out of that integral. You've got U infinity over that viscosity to the 4/5. And now you're integrating. Oh. I also had this x over here, so don't forget about him, as I almost did. So now that would be to the, so it'd be x to the 4/5 over x. Right? And wouldn't that just be x to the negative 1/5? So I'm going to erase that, put x to the negative 1/5. All right, and so next time we'll write the answer to what that integration is. So the actual integration isn't that bad. You know, you got a lot of constants that come out of the integral. Actually, I'll go ahead and this ends up being, if I said that all of this, let's call this C. Right? Then this would be 5/4 of C times x to the 4/5, but it would be integrated from L plus B, from L to L plus B. And if I did the math, I would end up getting 69.6 watts per meter squared Kelvin. And that is that average H value from L to L plus B. So that's not the final answer, but we worked so hard for it. So I am going to put a little bubble around it, and we will finish up tomorrow. Yeah? Not finish up, but we'll continue tomorrow, okay? All right. Y'all have a great day. I will see you tomorrow, okay? Thank you. Would you say it's the hardest unit? Don't think of it as the hardest unit. I guess it's, you know, there's a lot of stuff here, and especially like, you know, if you read chapter 6, there's a lot of stuff there, a lot of stuff. Tell yourself it's not as hard because you've got all the equations there. It really is. It comes down to figure out if it's laminar or turbulent, and figure out if you're talking about a local parameter versus an average over maybe the whole section or a particular little section. Hardest is relative. All right. Y'all have a great day. I'll have office hours at 5. Hope to see you there. All right. Thank you.